So today we're going to talk about linear regression. And the idea in this is that given some x input, that we can predict a y. So our predictor is going to be, in this case, a line. And we're going to predict a y value. Given an x value, so given an x value, say x1, we're going to predict a y value y1. And our predictor is going to be this function here, c0 plus c1 x1. And, or rather, c0 plus c1x. So there's our predictor. Now, if we have 2 points, let's suppose we have the points 1, 1 and 2, 2. Now let's make it 3, 3. Okay, it's clear that we can put a line through those points. And to do that, we'd basically solve this equation with x. So we'd write our equation c0 plus c1, and x would be 1, and y would be 1. Oops. Y would be 1, and c0 plus c1, x is 3, y is 3. And we could write that equation in a neat form with A being a matrix, AC equals Y. And the A matrix would look like this, 1, 1, 1, 3, C0, C1 equals, in this case, it would be, instead of Y, we'd have 1, 3. And we could invert this matrix A to the minus 1A, and that would give a diagonal matrix for C, so that would be a solution, and we'd have A to the minus 1 Y. And in this case, A to the minus 1 is 3 minus 1 minus 1, 1. And I happen to know that we need to scale it by 2. And so this would be our solution. And in this case, if we multiply this out, we'd get 3 minus 3, 0. So C0 would be 0. And C1 would be minus 1 plus 3, that's 2, divided by 2. C1 would be 1. And we know that's true. This would be a line going through 0 with a slope of 1. Okay, now, that's all and well and good. But what now if we have another point? Let me suppose we have the point 2, 3. So it's clearly not on that line. And the question is, what's the best we can do now for putting a line through, in this case, 3 points, but eventually we want to do any number of points that are not collinear. So let's rewrite this equation, AC equals Y, for these 3. And what we get now is we get first the point 1, 1. So that's x will be 1. And I'm going to get 3 entries now. I'll always have 1 in the first column, and then I have C1 times x, and x will be 2, and in this case, 3. C0, C1. This is what we're trying to solve for, and in this case, we have this matrix 1, 3, 3, or rather vector 1, 3, 3. Now it's clear that we can't solve this for this right-hand side, And the question is, what right-hand sides can we solve it for? So let's draw here some axes. Okay. And from our linear algebra, we know that these column vectors determine the solution. And what I mean by that is C0 always gets multiplied by this first column here. So C0 times this vector and C1 times this second vector determines a vector space. So what I'm saying is, here we have a three-dimensional vector, 1, 1, 1. So that's in R3. So that's some vector. I'm going to draw that, and it goes through 0, and it'll be some vector like this. Call that A1. And this second vector, 1, 2, 3, will be another vector in 3D space. Call that A2. So together, these two vectors now determine a plane. And we can reach any point in that plane by combinations of A1 and A2 times some multiple. So A1 times, for example, C0 plus A2 times C1 gets us to some new point in the plane. For example, if we added the 2, we'd get to a new point out here. So in general, this determines some kind of plane in 3D space. And so long as any right-hand side lies within that plane, we can find a solution. But in this case, it's clear that this right-hand side doesn't lie in that plane. So for example, here, our right-hand side lies somewhere here, and it's out of the plane. Now, what we can do is, let me suppose I drop a perpendicular onto that plane. Then this point is clearly the closest point in the plane to our right-hand side. Yep. So what I'm asking here is, I'm asking, okay, what right-hand sides can we solve for? And our answer was, well, anything in that plane of A1 and A2. But now I have a right-hand side that doesn't lie in that plane. So let me call this right-hand side, for example, let me call this right-hand side B. And B doesn't lie in the plane. So here's B. But I can get a projection of B. And so now B would be equal to that projection, and we'll call this some error. This vertical part we'll call an error. And let me call the projection, I'll call that B parallel. Okay, because it's in the plane. So now what I'm doing is I'm writing this right-hand side as being, instead of B, I'm saying, well, it's B parallel plus some error E. And these are vectors, and I'll just put a little squiggle to show that they're vectors. Now, what do I know about E? Well, I know E is at right angles to the plane. This is a right angle. So it's at right angles to any vector in that plane. And in particular, it's at right angles. So E dotted with A1 is equal to 0. Or E dotted with A2 is 0, or any combination of A1 and A2. But in particular, this is true. So now what I'm going to do is I'm going to write this right-hand side in this way. And what I notice is that another way of writing this is I could write A1 as a vector like this, and A2 like this, and E like this, E2, E3, it's a vector in 3 space, and that would be 0. But I noticed that this is just A transpose. So let me take the transpose. So if I take A transpose, A, C here, and take A transpose of B, that's equal to A transpose of B parallel plus A transpose E. And we know A transpose E is 0. We've just proved that here. So if I just take A transpose of the right-hand side B, then it's equal to B parallel. I'm going to get this point in the plane. I'm going to get that solution. And that is an approximate solution, and it's the best solution we can get to our point that lies outside the plane. So this is going to be our formula that we're going to apply to solve C. Let's take a look. Okay, so let me clear some space here. And we'll see how this evolves. Now I want to do this not just for the particular points I've chosen here, but let me write this in general. So what I'm going to get is, instead of A being like this, we're going to get A that looks like this. This will be x1, x2, x3, and if we had other x's, they'd be down here, and the y would look like, so these would be our y's, and that's what we're calling the vector B. But now let's take a look what A transpose is. So A transpose, let's come up here, is the vector 1, 1, 1, x1, x2, x3. So there's A, and A transpose is 1, 1, 1, x1, x2, x3. So this is A transpose, this is A. Now we have C0, C1 that we're trying to solve for. And on the right hand side we have A transpose. As many x's as we need. And this would be y1, y2, y3, etc. I'm just going to show the 3 points here. But let's multiply this out and try and solve it. So now we have 1, let's take the first row, and we're going to dive it onto the first column. So we get 1 times 1 plus 1 times 1. So if I had n of these down to xn, that first would be n. And now dive this down, and this would be sum of xi. And now this bottom one, x1 times 1 plus x2 times 1, this would be sum of xi again. And then finally we have x1 times x1 plus x2 times x2. This would be the sum of xi squared. C0, C1. And on the right hand side we have, first would be sum of y, and the second would be the sum of xi times yi. Okay, let's multiply that out. So I'm going to clear some space here. Let me clear some space down here. And I'm going to clear that edge off there. Okay, so let's see. Now I get n C0 plus sigma xi times C1 equals sigma yi, and I get sigma xi C0 plus sigma xi squared C1 equals sigma xi yi. Multiply this first equation. So we can see if I knew C1, it would be easy to calculate C0. It would just be this term minus this xi divided by n times, xi times C1 times divided by n. So that equation would give me C0 quite easily if I knew C1. So let's focus on eliminating C0 and calculating C1. So multiply this first one by xi. So this becomes xi squared, and here xi. And multiply this second one by n. So we get that. Now let's subtract this first equation from the second equation. So these terms are going to cancel out. These go. And what I'm going to be left with is I'm going to be left with n sigma xi squared minus sigma xi all squared times C1 equals n sigma xi yi minus sigma xi sigma yi. And that means that C1 is going to be equal to n times sigma xi yi minus sigma xi sigma yi, all divided by n sigma xi squared minus sigma xi all squared. So that's my C1. And I can then substitute back into this equation to get C0, and C0 would be equal to sigma yi minus sigma xi wait a minute, this was sigma xi yi. No, sorry. This was sigma yi over here, and this was just a sigma xi. Yes. So we take this across over here, and we get C1 times sigma xi, and all divided by n. So these are our two equations. Okay. And that's a very neat way to prove these. We could have done it by looking at the errors and calculating a least square error. So, for example, here, this would be our predicted y, and the actual y would be not this. So, let's suppose we take the actual y. So this would be, let's suppose this is y bar, the actual y, and if we squared that, that would give us the error. So we need the sum of these yi, and we'd substitute this for the predicted and this for the actual, and this, if we minimized this, then we'd get the same answer here. So minimum of this would give us a least squares approximation. So we'd get a line that had the least squares error. Okay, so you're going to program in these two equations. So these that are highlighted here, and that will give you the best fit line in a least squares sense. Okay.